Thank you very much for inviting me to give a talk at this conference. So I will present a joint work with Udi Ruchowski, François Lezer, and Jignieye. The basic motivations was a question about Berkovich spaces, but essentially we handled this by working on the model theoretic avatar of the Berkovich theory developed by François and Udi. And since this is a model theory conference, I will work in this frame. So the situation is the following. I take K, an arbitrary algebraically closed non-trivially valued field, so a model of ACVF. And when I will mention definable sets over such field, it will always be definable in the sense of the language with the three basic sorts of valuation theory and the enriched with the geometric sort defined by Haskell, Ruchowski, and McPherson that ensure elimination of imaginaries. So definable will always be in the extended sense. And I take X, an algebraic variety over K. And then to such a variety, François and Udi assign, Ruchowski and Lezer, define what they call the stable completion of X, so the X hat, which is a K prodefinable set. And I'm going to describe its L-valued points for L, an arbitrary model of ACVF containing K. So X hat, so if L algebraically closed valued extension of K, then X hat of L is the set of all stably dominated types over this field L located on X. So it's just a set of types, but part of François and Udi's work consists in first proving that this set is in fact prodefinable. So stable domination is a general notion in model theory, but here in this specific case, it's quite easy to understand what it means. So here, stably dominated means that definable and orthogonal to gamma. So by gamma, I mean the value group. So it means that first the type is definable, and then it does not extend the value group. So when one works over a given L, the value group will be the same as that of L for such types. And let me also say that so it's prodefinable, and in fact X hat is definable, and not only prodefinable, is definable as soon as the dimension of X is smaller than 1. But starting from a higher dimension, this is not definable in general. This is only pro-definable. For instance, let's just say that if one takes for X the affine line, so if X is the affine line, X hat of L is just the set of all generic points of balls, including the single element balls with valuative radius infinite, with infinite valuative radius. And this is definable in the language with the geometric sorts. But it's already quite huge. It looks like, because it's the set of all balls, so it looks like a very huge tree. But nevertheless, it is definable. And in general, X hat of L is not easy to describe. It's pro-definable. And this is the model theoretic avatar of Berkovich, of the Berkovich space associated to X when K is equipped with a real valuation. But here I don't care about the valuation of K. It can be of a very, it can be on, it's not a real valuation, not necessarily. Okay, and so this X hat can be, X hat of L has also a topology. Has a topology. So it's the closest topologies satisfying the following conditions. So if U on X is a Zariski open and f is a regular function, and u and f defined over L. Then valuation of f from u hat to gamma infinity of L. So by this I mean that this is the value group of L star together with infinity is continuous. So perhaps just a few words. I'm looking at u hat of L consists of types that are orthogonal to gamma. So it makes sense to consider the valuation of a function at such a type, and it lies in the value group of L, not in a larger group. So it makes sense. So really, val f is a well-defined map from u hat of L to gamma infinity of L, and the topology is such that this map is continuous. That one being endowed with the order topology. So we have a system of topological spaces, depending indexed by this valued extension of K. And so these sets can be quite complicated, but inside them there are very interesting subsets which are more tractable and are also very interesting from the viewpoint of the description of the homotopy type of X hat, but it will not be the point of this talk today. But there are interesting subsets of X hat, the so-called gamma internal subsets, which are also called skeletons in the Berkovich language. So this is why I use skeletons in the title. Gamma internal means that they are pro-definably, say, isomorphic and often even homeomorphic to some definable subset of gamma infinity to the n for some n. And in fact, in this talk, usually gamma to the n will be sufficient. We will not need infinity because we will only deal with the Zariski-Dance points. But general definition of gamma internal subsets. And now, let me give you a first example of such a set. So take X. Take for X, say, the multiplicative group to the GM, to the nth power. And then, let me denote Sn. It's a subset of GM n hat, defined as I describe its L-valued point, is a set of all generic points of n balls, of L balls of dimension n, I mean, n balls if you want, L n balls, with radius in L. So and centered at the origin. Sorry? Yes, in gamma of L, of course. Thank you. In gamma of L, centered at the origin. So which means basically that for every gamma 1, gamma n in gamma of L to the n, there is one element, corresponds one element of sigma n of sigma n of L, namely the generic point of the ball with radius gamma 1, gamma n. It's clearly definable if you look at if you try to describe the evaluation, the valuation of a function. It's given by a very simple formula, the minimum of the AI plus something like that, just using the coefficient of the polynomial, and the value group is the same as that of L, and so in fact one gets that way a definable homeomorphism between this sigma n and gamma to the n. So this is the first example of a gamma internal subset. And it is, this gamma internal subset is quite nice, quite comfortable to work with because of two properties. In fact, sigma L has two properties. It consists of Zariski generic point. I mean that for every L and every point of sigma n of L doesn't lie on any proper L definable Zariski closed subset. So for every L, it is generic with respect, Zariski generic with respect to L, and it is also a Biancar, a type you can see it at so when you have a type which is a Zariski generic, you can see it as the valuation on the function field of the variety over the field L, and it will be a Biancar as an extension of the valuation of L. It consists of a Biancar valuations. So it's a gamma internal set and with nice properties, nice geometric properties and nice valuative properties. And now let X now be an arbitrary algebraic variety over K, say for simplicity irreducible and n dimensional, and let U1, Um be Zariski open subsets of X. I take them non-empty, so dense. And I take finite maps, phi 1, Ui to Gmn, phi m, Ui, Um to Gmn. Finite maps. Then what we prove is that, then, if I denote by sigma, by definition, the union of pre-images of sigma n is a gamma internal subset of X hat consisting of Zariski generic and a Biancar points. So I proved this kind of result in the Berkovich setting, but in fact the proof more or less translates into this model theoretic setting, and in the paper with François Audy and Vincent, we write the precise translation of the proof in this setting, and we first prove this. And in fact, the way to describe this as a gamma internal subset is very pleasant. So more precisely, there exists G1, Gn non-zero rational functions on X. So since sigma consists, the fact that sigma consists only of Zariski generic point is very easy. It's just because it's the case of sigma n and all maps are finite. So once a point is Zariski generic, you can evaluate at this point any rational function because the point is not a pole. And so val G1, val Gn induces a definable homeo between sigma and a closed K definable subset of gamma to the n. So first one doesn't need infinity because everything is Zariski generic, so there will be no vanishing of the functions. And then this description of sigma as gamma internal, so as abstractly homeomorphic to something living in the hominimal world, is in fact quite concrete. It's given by finitely many rational functions. So the theorem says that there is such functions. So now, once we have this, moreover, for every non-zero rational function on X, when I restrict the valuation of G to sigma, it is definable. And continuous, of course. And continuous. So now the problem we were interested in is the following. We have this nice gamma internal subset, which we can see using val-G, using these functions. We can even think of it as a closed definable subset of gamma to the n. And then we have a collection of continuous definable maps on this hominimal set, which are very natural and come from algebraic geometry, namely the collection given by all val-G for G non-zero rational functions. And so what can we say? So let, okay, I don't know, I will, okay, let lambda, I remind the ground field as an index of sigma denote the set of all function like this, with G as above. And so what can we say about this set? And our main results say the following, then theorem. So what is clear is that it is a group, because of course rational functions, you can multiply them, and so the valuation will add. So the fact that it's a group is not is clear, but lambda k of sigma is a group. This is obvious, but which is not obvious is stable under min and max. So this is the first point. And then there exists, more or less, it is finitely generated in some sense. There exists H1, HL, non-zero rational functions on X, such that such that lambda k is generated by the valuation of the hi restricted to sigma, of course, and the constant, say gamma belonging to gamma of k, under the operators plus, minus, so and min and max. So I don't know what is the technical term, perhaps lattice group or something like that, but as a group equipped with min and max operator, it is finitely generated up to constants by rational functions. So this is the main theorem of our paper. And I would like to explain the part of the proof, at least I think that I will fully prove one, which is, and then try to explain the steps or some ideas behind the proof of two. Two is more complicated, but it's not so easy to give the full proof during a talk. And so this has a Berkovich counterpart where gamma internal is replaced by a piecewise linear subset or skeletons of a Berkovich space, and we have exactly the same theorem. Gamma to the n is replaced by the just R to the n in the Berkovich setting. Okay, so now let me try to explain the proof of one. So first, by model completeness, we can deal only with the k-point of sigma and prove that if I have if I have two functions in this, the min and the max. And since it's clearly a group, it's sufficient to deal with the min. So stability under plus minus is clear, and it is sufficient to prove stability under mean. So now let, I don't know, let, H prime belong to this, and let X belongs to sigma of K. Then I distinguish two cases. If, and let lambda belongs to K with valuation of lambda being 0. Now, if val f of x is not the same as val g of x, it's h and h prime, then the valuation of h plus lambda h prime at x is just the mean. Is the mean. Is the mean of veil h of x, veil h prime of x. So in this case, everything happens well. Now, if this is equal, then the same unless the image under the residue map of h of x divided by h prime of x. Now they have the same valuation, so the quotient is of valuation 1, so I can reduce, is equal to, I think, a minus residue of lambda, or something like that. Okay? So this is the only bad case. I mean, my idea is to try to realize this mean as the tropical function, as the minimal function associated with h plus lambda h prime, and at almost every point it will work, unless at some points where I have such things like that. Now, how can I get rid of such things? Then now, let say, I don't know, psi from sigma of k to the residue field of k, defined as x maps to minus residue of h of x divided by h prime of x if this belongs to the residue field of k, and of course if val h of x equal val of h prime of x, and if this belongs to the residue field of k. So if I have these two conditions, I send x to the bad scalar, to the bad element of the residue field, and to, say, 0 otherwise. I don't really care. So note that the residue field at a point of this sigma, the sigma does not increase the value group, but it increases the residue field. In general, the residue field will be an n-dimensional extension of the residue field of k. So in general, elements tend not to belong to the residue field of k, but it might happen that they belong, and then I take this. Otherwise, then this is a definable map from sigma of k, a k definable map from sigma of k to gamma of k, but to the residue field of k, sorry. But this is gamma internal, and gamma and the value group and the residue field of a given field in ACVF are orthogonal to each other. So there are basically no non-trivial maps between something which is modeled on the value group and something which is modeled on the residue field. So by orthogonality between value group and residue field, so psi is perhaps not constant, but piecewise constant. Psi takes only finitely many values. So there exist some lambda. Of course, residues of, since residue of k is infinite, I'm dealing with algebraically closed field, is infinite. there exists some lambda in K. Valuation of lambda equals 0. And residue of lambda does not belong to the image of psi. And then such a lambda does the job. Then val of h plus lambda h prime restricted to sigma is then equal to the mean of val h prime restricted to sigma. So this proves stability under mean, and then since this is also stable under minus, this is stable under max as well. So this gives the full proof of the part 1 of the theorem. Now for the part 2, I will try to describe the steps, but I will not be able to give all details, of course. Ah non. Voilà. J'ai essayé de faire monter et descendre des tableaux en même temps, mais ça, il ne faut pas. Mais, ah ok. C'est ça. Ah si, c'est bon. Okay. So now let me try to explain what are the main steps of the second part of the theorem. So now proof of do sketch. Basically we start from this function g1 gn that induce an embedding, a definable embedding from sigma into gamma to the n. And what I didn't say, but I didn't write, but I just say it, is that once I have such a set of functions, of rational functions, I can enlarge it, and the property will still hold. And in fact, what I will do now will be enlarging this set of rational functions inducing an embedding to improve the properties of the embedding. So first of all, one enlarge the family. G1, Gn, so when I enlarge it, I doesn't destroy the first property, so that the following holds. Say for every L next valued extension of K, algebraically closed valued extension of K, I don't write it, but L is always for such a thing in this talk. For every G rational function on X, but that one defined over K. There exist finitely many functions. Okay, H1. I don't know per. Okay, I don't want. Okay, E1, ER belonging to the group generated by the GIs and the constants in K star. such that for all x in such that for all x in sigma of L, there exists I with g of x, with val g of x equals val of I of x. So essentially, what I am proving is that there are functions, so there are finitely many rational functions, so I can enlarge my g1, gn, such that when I look at the map induced by a given rational functions, it always piecewise belongs to the group generated by this fixed set of rational functions and the constants. So this is a weak form of the theorem I want to prove it, because here not only I want the function to belong piecewise to the group generated by those guys and the constants, but I want the function to be expressed as a combination using min and max. Here I'm not claiming such a thing, just claiming that piecewise my function g belongs to the group generated by this. And how does one achieve this? In fact, by compactness, it is sufficient to prove that one can choose G1, Gn, so that for every x, for every L, for every x in sigma of L, and I just look at what happens at the set at x and not at other points, the group of the set of the set of val g of x for g a non-zero rational function over k on x is generated by the val gi of x and the constants. So I replace the problem of having a function belonging nicely piecewise on the whole gamma internal subset by a problem at a fixed point, but of course I have to allow the valued field to be arbitrarily large to make to be able to use compactness. So in fact, I'm interested, this is in some sense, I want to control the group of this point on sigma of L induces a valuation on the rational function field of my original variety x over k, and I'm looking at the value group of this valuation. And I want to have a uniform control of this value group, namely being able to exhibit functions that generated, finitely many functions that generate this value group modulo the constant for every point of sigma of L and for every valued extension F of x. And so I will not describe precisely how we do this, but this is not very difficult. In fact, so I will mention the main ingredients to do it. So in some sense, it means that we have to find a smart definable way to express the fact that some rational functions will have this property. So we have to, in some sense, to find definable formula, to find formulas in the language of valued field, ensuring that a certain finite family will generate a value group, but not of an arbitrary valuation, of a valuation induced by point coming from sigma of L. And there is essentially two parts. There is kind of an explicit. So one is interested in the value group, but one first try to make explicit computations about the residue field. Of such valuation, and the key fact being that the residue field at the generic point of a ball, but not with radius in the ground field, with arbitrary radius, point of a ball, is purely transcendental over that of k. Because remind that sigma is defined using three images of this sigma n over L. So points of sigma are related to balls over L. And when I look at the valuation induced over k, I get the valuation induced by the generic point of a balls, but the radius belongs to L, and so not necessarily to k. So the residue field can be more or less arbitrary between k and k parenthesis t1, tn, but it's always purely transcendental. So this is the point. This is the first point. But I'm not interested in something about the residue field. I'm interested in something about the value group. And the way to relate one to each other, the computation at the residue field level will be sufficient because of the fact that Abyankar extensions of k are defectless. So with a good control on the residue field, we get kind of a partial control on the value group. But then, since in this case the Abyankar inequality will be actually an equality, this will be sufficient to ensure that with our given finite family, we have the whole value group. And the fact that Abyankar extension of an algebraically closed field, or in general over a defectless field, are defectless. This is due to Franz Victor Kluman. It was perhaps proved in some particular cases by other authors in various settings, but the first general proof is due to Franz Victor. And we also give in this paper a new proof of this, which is model theoretic, because it is consistent with our framework. But the original proof, which was more algebraic, is due to Franz Victor. And this is the key point of this. So this is essentially valuation. Some quite down-to-earth aspects of valuation theory with explicit computation, and this fact which is not obvious at all, and this helps us to get this first finiteness result. Now, the second step. So now our embedding, so our G1 Gn not only induces an embedding, but an embedding with this property, and this remains true if I enlarge the family once again, obviously. Now, we enlarge. We know, and I will explain, of course, it's I describe what we want to do, but we now enlarge G1 Gn so that for every G non-zero rational function on X, defined over K, the valuation of G restricted to sigma, which I see as a map from sigma to gamma, is Lipschitz. I will say what it means, is Lipschitz, when sigma is identified through val G1, val Gn, to some subset closed definable subset of gamma to the n, and by Lipschitz, I just mean that a function is Lipschitz. I just mean that okay, let's say that psi. If I have d inside gamma to the n, psi from d to gamma is Lipschitz. If and only if there exists some an integer such that psi of x minus psi of y is smaller than a times the maximum of xi minus yi. So this is really just the usual Lipschitz condition. The value group is arbitrary, but the constant is an integer. So it's Lipschitz with respect to the usual notion of order of magnitude. There are no infinite elements involved in the Lipschitz definition. That's crucial. So how do we ensure such a fact? So I want to prove that there exists G1, Gn such that our things is Lipschitz. Of course, by model completeness, I can do it over any submodel of K over which everything is defined. So first of all, we can assume that K is finitely generated over the prime field, which I do not really care, but what I care is that, in particular, gamma of K has finitely many convex subgroups. That's the point. For this part of the reasoning, I need to have a ground valuation with a finite height, finite number of convex subgroups. Then I told you that I can choose G1, Gn inducing an embedding. This is true for any valued field. And so I can then, by enlarging G1, Gn, I can assume that val G1, val Gn restricted to sigma of K prime is injective for every coarsening K prime of K. What do I call a coarsening of K? I take the same underlying field, but I quotient the valuation by some convex subgroup here. So it's just a coarsening of the valuation. And since for every algebraically closed valued field, I am able to find finitely many functions inducing an embedding, and once some function induce an embedding, I can add to them arbitrary functions. I do it, and I can do it because I have finitely many convex subgroups, so I have finitely many such fields to consider, and then I take, and the underlying field is always the same, so I just need to, I will always have rational functions over this field, and I have this. Now, once I have this, ok, donc lui, je le monte. Once I have this, it's almost done, and I will explain why. Now, this property of being injective for coarsening, again, by the general model completeness or things like that, it transfers to arbitrary algebraically closed valued extension of K. And now, no matter whether they have a finite height or not. So this implies that for every L algebraically closed valued extension of K, and every coarsening L prime of L with the same definition of a coarsening, val Gn from sigma of L prime to gamma of L prime to the n is injective. Then I take such an L, I have my map sigma of L, gamma of L to the n, with val G1, Gn. Here I have, since this is a coarsening, I have a specialization map defined at the level of the whole stable domination space, but I just look at it. Here I have the same, gamma of L prime to the n, and I have also a specialization map. And if you look at what it means, these injectivity properties, this means that if x and y belongs to sigma of L, then the specialization of val g1 gn of x is equal to that of y, if and only if the specialization of x is equal to that of y. This is what this injectivity tells. Because in some sense, one of the implications will just be commutativity of this diagram, which is very general, and the other way is this injectivity property at this level. And then now we are done, because this exactly means this is equivalent, the fact that it holds for arbitrary L and arbitrary coarsening, this is equivalent to the Lipschitz property. You can... Why? Because, as I said to you, Lipschitz property is essentially something about compatibility of the order of magnitudes, and then this is precisely what is encoded in this notion of convex subgroups. So the convex subgroups are rarely designed for purpose of comparing order of magnitude, and this Lipschitz property, so it's translated in a pure, so one gets Lipschitz property by dealing with a little bit model theory and things about coarsening of valuations. And now we are almost done. Why are we almost done? Because now everything will happen in the DOAG setting. There is no more valued field, no more stable completion or whatever. Because now we have a very nice embedding of sigma into gamma to the n. Modulo this embedding, every rational function is a Lipschitz function, and that belongs piecewise to the group generated by the coordinate functions. And what I want to prove now is that this function is can be expressed using the coordinate functions through the operators plus, minus, min, and max. So now the problem is purely DOAG. I have a continuous definable Lipschitz function which belongs piecewise to the group generated by the coordinate functions, and I want to prove that it in fact belongs to the set of functions generated by the coordinate functions under these operators. And that's in some sense the final theorem of this paper. So now the conclusion now comes from the following theorem. So to emphasize that this is really purely DOAG, I will even change the notation, no more gamma. So let G be a model of DOAG. Let D be a definable subset. Let F1 Fn be some Q-affine maps from Gn to G with constant term belonging to some model, say some model G0 of DOAG, and let phi from D to G be a G0 definable, continuous, and piecewise Lipschitz and piecewise equal to some of the Fi's. Then phi belongs to the set of functions generated by the FIs, the coordinate functions and constant in G0 under what I plus minus min and max. So this is a theorem giving a sufficient condition for a continuous function, continuous definable function to be expressed as a min-max. Not necessarily a min-max using only the basic functions with which it coincides piecewise. Okay, sorry. Yes. This is a purely DOAG theorem, and I will not have time enough to give its proof, just say the ingredients and perhaps give some examples, just one or two examples, but just the proof. So there are basic proof. First replace D with its closure. Everything will still hold, so D with closure. This is harmless. So now D is closed. And then now reduce to the case where D is definably compact. And then for this one, enlarge G. So one want to enlarge the model G to have infinite elements and intersect with a huge ball. This will give something which will be definably compact on a bigger group. Then, of course, the function we will get will involve perhaps elements in the bigger group. There will be the radius of the ball or something like that. So we might get something which is not a G0 definable, but definable over something a little bit larger. But then one has to work slightly to prove that, in fact, everything can be, we can make the parameters belong to G0. And then use cell decompositions and separation hyperplanes between cells to get, in some sense, an explicit description with min and max. So, because it's flip sheets. Because it's flip sheets. So maybe let me just make some comments. So of course, it's to be a plus minus min max function, it's necessary to be Lipschitz. Plus minus min max combination of affine functions, it's necessary to be Lipschitz. So now it's in fact sufficient. Let me also tell that we prove in the paper. I don't think that we use it, or perhaps inside the proof, but we also prove that in fact this will be automatically satisfied as soon as D is convex. If you have a continuous definable function on a convex subset of G to the n, then in fact it will be automatically a min-max and so automatically Lipschitz and so on. Let me now perhaps just show you very simple examples of functions that are not Lipschitz to see that I mean this is not an empty or an automatic condition. So I can give you a non-compact and a compact example. So example of non-Lipschitz function. So I am in R2 now, and I take 1. So now my D, so it will be non-convex. It's like this. This is my D, and as a function, I will take here, I take the function x. Here I take 0, here I take 0. This is certainly definable and continuous. but cannot be Lipschitz because you see that very far the difference between the two values of the function at 2 points will not be bounded by a constant. So this is the non-compact version. Non-compact version. And the compact one needs infinitesimal element, compact version. But here you have epsilon. Here, sir, you have a, and here also x 0, but with epsilon. Over when you have, then the function like this will not be Lipschitz and will not be a min-max. Okay, I think I'm done. So thank you very much for your attention.
Thank you very much for a lovely talk. Are there any questions?
Yes?
How's it with the microphone?
So it seems like you don't use much the actual form of sigma that you presented.
No, and in fact, I use this form of sigma for originally for one reason, because I was started with the Berkovich space in which I really needed to have some skeleton defined algebraically. The only way I know in the Berkovich setting to define algebraically skeletons is to use this kind of construction, and that we transfer this construction in the François Andodis setting. But then we prove also in the paper, I didn't say it. In fact, this form is quite general because if you have a gamma internal subset consisting of generic points and Abyankar, then it embeds in such a sigma. So always. So in fact, this is in some sense the archetypal example of a reasonable gamma internal subset.
Thanks.
More questions? Otherwise, we'll have more questions over coffee, unless I'm not seeing any of you. And we'll resume at 5 minutes to, so at 25, that's what I mean. At 25.
Thank you very much.